So I'll talk today about contrastive explanations for reinforcement learning. So it would relate to some of the stuff Sarit was talking about in the first talk. And I should apologize that it's not really a lot of multi-agent stuff, but it will be a little bit multi-agent. So in general, and Sarit talked about some of it, why do we want to do explainable AI? In this context, explainable reinforcement learning. We want to improve people's understanding of the agent such that they can do things like decide whether to give an agent autonomy, select between different policies maybe, and of course collaborate with the agent, Sarit mentioned. So this is kind of our goal. And what I'll talk about today are two works where we try to do contrastive explanations. And the motivation for that is that people, when they explain, they often like to have something contrastive. So if I ask you, why did you go to Bar-Ilan? Maybe you'd say, why did you go to Bar-Ilan and not to Tel Aviv University? And those who work in explainable AI might know Tim Miller's work on kind of what can explainable AI learn from the social science. And one of the lessons is that contrastive is people like it and understand it properly. And so the first work I'll talk about is about contrastive explanations between different agents. So this is the multi-agent aspect. And the second one will be more single agent, but how to show alternative in a single agent policy. All right, so a bit of background, and this was also briefly mentioned by Sarit. So in the first work, we really extend this idea of policy summaries, where the idea is to give a global explanation of how the agent acts in different parts of the state space. And so, for example, here's a video of Michael Jordan, say that he's my agent. And I can tell you, if you want to understand his capabilities, I can tell you, you can watch a full NBA season, 81 games, but it's not very efficient. So maybe I can do this sort of summary of highlights of how he scores and how he defends and how he passes the game. Okay, so that's kind of the key idea. So I think this was the baseline sort of in Sarit's work, this video-based demonstrations of the agent. To be more formal, all of you, I think, in this audience know MVPs. We have states, actions, transition function, reward function. And here we're not trying to train a policy, but rather we have a policy as an input and some budget for how long this summary can be, how much information I can show the person. And the output, the summary, is really a set of trajectories or state action pairs that shows what the agent is doing in different regions of the state space. And the key question is really, what information should we show in this summary? What would be useful for the person? And different approaches have been proposed. So some works looked at important states, where the idea is that the state is important if the decision that I make in that state has a large effect on the future outcome. A different approach used a kind of policy summary, generalization approach, where the idea is that I want to show you a subset of states that if you would extrapolate from them, you would be able to best generalize the full policy. There have been other approaches looking at global and local minimum and maximal states and things like that, frequency of visitation, a lot of different things. But what I want to say is that all of these approaches are summarizing really a single policy independently. And in this first work, what we try to do is kind of address that. So if my goal, or if the user's goal, is to compare alternative policies, say that you're going to buy your autonomous vehicle and you want to choose which driver style to take. So now I have both Michael Jordan and LeBron James, and you want to see where they diverge, then I would argue that if you have independent policy summaries, that might not be good enough, because, for example, maybe in the important states, they always agree, or something like that. And we can utilize the fact that we know that this is your goal to show you where the policies diverge, okay? And then the question is, what information should we show? I'll skip the video, but here you will see LeBron James and then Michael Jordan. And the question is how to compare them. Show one done. Yeah. So now we've seen two agents. And we call this disagreement-based summaries. This is work led by Amitai, who's a PhD student in my group. And the key idea is very simple. Basically, what we want to show you is disagreement. So here I'm going to use a highway simulator where the agent controls this green vehicle. and there are other vehicles on the road, and say that I have one policy that keeps driving in the left or top lane, and I have one policy that switches to the right lane, then maybe that's a difference that the user would be interested in seeing. Okay? So how does the algorithm work? It's pretty simple. We simulate both policies. We assign one agent to be the sort of leader, so we start with their policy, and they both take actions. And as long as they agree, we just continue. Once we reach a disagreement, so say one agent continues straight and one agent switches lane, we let them diverge. We let each of them, so we have now the black agent and the red agent, and we let each of them continue according to their policy for, say, case steps, and we record that. Okay, so we record these disagreements. Then, after these case steps, we bring back the agent, the diverging agent, to the same place as the leader agent, and we do that again until we reach the next disagreement. And this way we collect this sort of data set of disagreements. Importantly, we then switch roles, because maybe my policy goes to a totally different region of the state space. Say that I always drive in the right lane and the other agent doesn't. Okay? So we collect all of them, and now the problem is that we might have a lot of these disagreements, so we need to somehow rank them if we have a sort of limit on how much information we can show. Question?
If you split in trajectories, there is maybe an initial effect that's on the non-chosen policy. So the environment.
So each of them, you can think about it as like cloning the environment to a different one. You're right that things can happen differently stochastically on the other environment, but then we bring them back to the same place. So it's okay if you go a bit differently than me and stuff change in the environment. So now we want to rank the disagreements. I won't go into this very technically, but we tried different scoring functions where the general idea is kind of to measure the extent of the disagreement. Okay, so say that I think that turning right is very good and Ronnie thinks it's very bad. Okay, or as opposed to I think that turning right is very good and Ronnie thinks it's okay, but he just chose something a bit different. Okay, so we can kind of measure how much our value functions differ about this decision. And things like that. Okay? And then basically we have this summary which shows disagreements, and this is one domain we used in the evaluation. Another domain I'll talk about in the evaluation is Frogger. So we have frog trying to cross the river and the road, and again kind of the same thing, showing where they disagree. Okay, clear so far? And so we did two tasks for evaluation. One was an agent selection task, where the idea is we have ground truth. We know which agent is better because we have their scores, and we want to see if people can identify that from these disagreement summaries. So in Frogger, we had 3 agents that were used in prior work. One was an expert, one had limited vision, things like that. And we compared disagreements to highlights, where people see, instead of this one contrastive summary, they see 2 independent summaries with the important state. So they see the same amount of information, but either in kind of one summary that's showing both agents, or in 2 separate summaries. We had 74 participants, and the paper was accepted, so we did better. And so disagreements is in green here, and you see the success rates of participants, and here that's the different comparisons between agents. By the way, in prior experiments, we did have highlights perform pretty well, but it kind of depends on how different the differences are between the agents. Like, is the better agents really much better than the other agent, and so on. So we did see actual improvement in the agent selection test. The second test, the Frogger picture here, but it should be the highway. We had 3 agents in the highway, where the idea was, here it's harder to say what's better performance. I mean, it depends on how you define your reward function. And we wanted to see whether people can understand the qualitative differences in policies. So we trained different policies by changing the reward function. So we had one agent that prioritizes, for example, high velocity and keeping distance. And this was during COVID. So one agent was social distancing from other cars. And we had a fast right agent that drove fast in the right lane. And again, same conditions. And here we didn't see as much improvement. We only saw improvement. So what we asked people, I didn't say that, is about basically the reward functions of the agents. What does this agent prioritize? And here we only saw differences in one of the questions, and one of the agent comparisons was a disagreement one, but wasn't like a big win as we wanted, but we're still working on it. So to summarize this part, the main idea, and I guess this is where it relates to the multiple agents, is that if we want to help people compare policies, we can create summaries or explanations in general that are considering both policies at the same time and are not just independent. And then the second work I wanted to briefly talk about is taking this kind of same contrastive idea, but to the realm of single agent and local explanation. So these policy summaries were global in the sense that they try to convey the general policy and not a specific decision. In local explanation, what we try to explain is why the agent chose a particular decision in a particular state. And there are different approaches to doing that. There's the saliency map approach, where people kind of highlight where the agent's attention is at different states. I'll talk about this less. There's a causal approach where you build a causal graph and then try to understand that, but that requires more engineering. And then there's an approach called reward decomposition, where the idea is that if you have a reward function that you can decompose, so for example, think of the highway, I can define some reward for being in the right lane and some reward for driving fast and so on. And then you can learn Q values separately, you can kind of decompose that. And once you do that, you can, actually, initially it was done to improve training, not for explainability, but people have used it for explainability in the sense that then you can say, when I do the action explain, the Q value is composed of a little bit of driving in the right lane, Q value for future reward, high speed, and say change lane component gets a high value here. So that's supposed to help people see kind of which components of the reward are affecting the decisions and the predictions of the agent, okay? And what we did in this work, which is again with Yotam and also with Yael Septon, who was a master students in the group, is it's going to look very similar to disagreements, only now we don't have two agents. We have the agent and we have an alternative action that they didn't choose, right? Because really if the agent, learned Q values, then you can say what would have happened if they chosen a different decision except instead of the decision they did choose, okay? So we can show contrastive explanation about my own action, kind of. And the algorithm is again pretty similar. So basically, we need to decide what's the counterfactual action. So one choice, which we did in the experiment, is just take the second best action. But you can imagine having the user, for example, ask queries about what would have happened, why didn't you choose this other action? And then we simulate the agent with the counterfactual action, compare the simulated trajectory to the realized one, and again, we can rank the differences, for example, based on how different the value is at the state where they end this kind of simulation where we go forward. Okay, clear? All right. So we call it COViz, think counterfactual something visualization. And here we did another study with identifying the agent preferences, and we chose to compare with reward decomposition. The reason we chose that is that saliency maps we've seen in prior work and other people have seen it too. People don't understand them. It's like if you see the attention spread out, then people think, oh, it's good, it's looking at a lot of information, when it really means that they didn't learn anything and things like that. So that doesn't work. And the causal explanations are just complicated to create. You need to first model the environment, so it's not really plug and play. So we again created 3 different agents with different preferences, And the conditions were either just showing a summary, so no local explanation, just showing what the agent does. Either our new approach of showing this counterfactual trajectory, reward decomposition, or we also sought to combine them because we thought that they really communicate different and potentially complementary information. One is kind of showing you where the agents went, and one is trying to show you what they think and expect in the future. And we did 2 studies here. One was between subjects, so each participant sees one condition, so there's no learning effect or anything like that. And we saw that the combination actually helped quite a lot, seeing both explanations. That's the core option. There weren't significant differences between COViz alone or the reward decomposition. The summary alone was much worse in one of the agents, and it was significantly worse overall. And then we did another study where we had a within subject design, so each participant saw all explanation types. And the reason we did that is that we wanted to also ask their preferences, like Sarit showed in her study. And so first, the good news is that we replicated the fact that in terms of performance, how well they can identify agent preferences, they do better with the combination. And in terms of preferences, kind of similar to what Sarit showed, they actually didn't like it. So this is how many people ranked the combination first place, second place, or third place. And they really liked our new approach, even though they didn't necessarily do better with that. I think that aligns both with Rit's result and with other results in explainable AI in general. Like, you can't really rely on people's subjective preferences. So it's very important to do these objective tests. And so that was nice to see. I think also in general, I think something that we don't do enough is combine approaches. I mean, right, we need to write papers, so we invent a new approach and hope to show that it's better, but I envision at least an explanation system that has different approaches combined. So it was nice to see that it actually helped, which wasn't obvious because of the cognitive load that could be incurred with that. All right, so to summarize, basically in both of these works, we tried to see whether contrastive information helps people assess alternative policies, whether it's between different agents or of the same agent. And we saw that in general, it does help in this task. And I think in general, also, the way we evaluate explanations really depends on the context of the user's tasks. What are they trying to do? And maybe you can have different explanations types depending on what the goal of the user is. So if the goal was collaboration here, maybe something else would have worked better. And just very briefly, some things we're working on now. So one direction is more interactive explanations where we have people query the agent. It kind of relates to Sarit's logical approach, but to be different. We're starting to work on explanations for multi-agent settings, but I don't have anything to say now, definitely not more than Sarit. One recent result we have from really the last week is we have to use LLMs now because, so we actually, one of my students say we can have the LLM do a summary, and I was like, no, I don't think we can, but actually, if you have this captioner for states, it actually does pretty reasonable job for simple domains so far, with some algorithmic approaches. Some work with Reut on explanation for goal recognition, and related to this idea of collaboration, we have some work together with NVIDIA on a task where a person can decide whether to take over an agent and how explanations help or do not help to that. So thank you, and thanks to Yotam and Yael for this one.